with the 4 final talks of the day. The first will be by Mark Rychnovsky. So start.
Hi, I'm Mark Rychnovsky, and I'm going to talk about a recent work along with Evgeni Dimitrov for a GUE corners limit for a variant of the 6-vertex model. So the plan for this talk is first we're going to define the variant of the 6-vertex model we're interested in. Then we're going to say a little bit about why we choose to study this model, which is going to be novel limit behavior and the fact that we have exact formulas, which sort of allow us to study it. And then we're going to state the main theorem, which is a convergent result to distribution coming from random matrix theory. So just for a little bit of background, the 6-vertex model was introduced by Linus Pauling to study ice crystals in the 30s. It's one of the very heavily studied, one of the classic and very heavily studied models in statistical mechanics, and people can derive direct exact formulas for it. It's been used to study a variety of physical phenomenon, and sort of more recently, a special case of it called the stochastic 6-vertex model has become one of the primary discrete models used to study growing interfaces and KPZ universality. So let's define the stochastic 6-vertex model. This is going to be a probability measure on collections of upright paths in the upper right quadrant of the integer lattice. And we're always going to consider paths entering on the left and no paths entering on the bottom. So here we've drawn a possible collection of paths in blue. This model is going to depend on 2 parameters, b1 and b2, which are between 0 and 1. And the way that the probability measure is defined is first, let's restrict to an m by n rectangle. The rules for the paths are that each vertex can contain only one path. So you can't have 2 paths that share the same, each edge can contain only one path. You can't have 2 paths that share the same edge. And these are upright paths. We want to think of them that way. So if however many paths enter from the bottom and left of some vertex, the same number of paths have to exit from the top and right. And if you look at those 2 rules, you see that there are 6 possible things that can happen at a vertex in the integer lattice. And we assign a weight to each of these possibilities. So the weights are written below, 1, b1, b2, and so on. And then to give the probability of a collection of paths in some finite rectangle, you just take your collection of paths, you look at what happens at every vertex and assign the proper weight, and you multiply all those weights together. And that gives you the probability of achieving that collection of paths. So normally you would want to divide by some normalizing constant so that this sums to 1, but in this case it already sums to 1 because we've chosen the weights because the weights are chosen in a specific way. I should point out that there's another way of viewing this. You don't have to restrict yourself to a finite rectangle. You can also just view these paths as going off to infinity in the full upper right quadrant of the integer lattice. And the way you do that is by sort of building it up diagonal by diagonal. So if we imagine that I erase everything above this dotted diagonal line, and I've just sampled the paths up to this point, then if I want to sort of continue sampling along this diagonal, first I need to decide what happens at this vertex. And we know that no paths enter, so the only possibility is that no paths leave, and we have this empty vertex. Then I look at this vertex, 1 path enters from below, so we choose between one of these 2 things, and we just flip a coin with probability b1, and we get this one in the diagram I've drawn. And then we choose here, and we have 1 path entering from the left, so we choose between these 2 vertices. And we keep flipping coins, and they're all independent to fill in vertices along this diagonal, and then we simply move to the next diagonal and do the same thing. And this gives us a path moving out to infinity. This model was originally introduced by GUE and Spawn in 1992, or this sort of like special version of the 6-vertex model with these weights. And it was proven to have KPZ type fluctuations by Borden, Corwin, and Gorin in 2016. So that's the stochastic 6-vertex model. We're going to study a slight variant of it that will have interesting properties. And we're going to restrict ourselves to a height n infinite width rectangle, we're going to have paths again entering on the left, and paths entering on the left, and no paths entering from below. And we're going to record the positions at which the particles touch the upper boundary, or sorry, record the position at which the paths touch the upper boundary, and call those lambda 1, lambda 2, etc. And so now when we're going to define a weight for each collection of paths, and we're going to define it very similarly to the stochastic vertex model. We just take the product of all the vertex weights we defined earlier, the same vertex weights as before, but we're going to add in a boundary term, which is ft of lambda, which is just going to be some explicit positive function of the positions at which the particles touch the upper boundary, the positions at which the paths, touch the upper boundary. I'm not going to write it down because it's not particularly illuminating, but it's important that it's an explicit choice because that gives us our exact formulas. And in this case, because of this boundary term, this doesn't sum to 1, so we need to divide by a normalizing constant to get a probability measure. We can think of t should be thought of as sort of a time parameter. It's going to be some positive parameter you can think of as time. And when t is equal to 0, we're just going to get the usual stochastic 6-vertex model restricted to this rectangle. So this model was originally defined by Borden and Petrov in 2018 using a generalization of the Schur functions called the Spin-Hall-Littlewood functions. And it's an analog of the Schur process for that generalization of the Schur functions. And this analogy allowed Borden and Petrov to generalize some of the ways of deriving exact formulas from the Schur process to derive exact formulas for this model. So the fact that we have exact formulas is one reason why we chose to study this model. Another reason is that there's conjecturally novel limit behavior for this model. So if we take the height of our rectangle to be large and we take t to be large, so we're looking at many paths, this is a sampling of a path collection, and this is the conjectural phase diagram. And we see that there's sort of 3 regions where we have only one vertex type occurring with high probability. So here it's crosses in region 1, here it's horizontal vertices in region 3, and it's empty vertices in region 2. And then in this region there where you sort of have remaining randomness, the sort of liquid region, you get Gaussian free field type fluctuations for one piece and a cone with KPZ type fluctuations above it. And this is the only model we're aware of where you conjecturally have Gaussian free field type fluctuations and KPZ type fluctuations coexisting in the limit. And in particular, it would be very interesting to study what happens at this sort of conjectural interface between them. So this phase diagram is almost entirely conjectural at this point, and we're going to do something more basic. We're going to study the point 5, which separates 2 frozen regions, and try to sort of confirm the phase diagram near that point. So we want to study the point that separates all horizontal vertices from all empty vertices. And the way we're going to do that is look at the bottom few paths and look at the positions at which they take upward steps. And so we'll call the collection of paths pi, and we'll call the positions they take upward steps lambda of pi. And there's some superscripts and subscripts, but we're thinking of all of these as horizontal particle positions, as we've drawn sort of the red dots, the upward steps as particles. And the main theorem is that if we suitably recenter and rescale these positions of upward steps, the lambda of pi's, then the limit as t goes to infinity is the GUE corners process, which is a process coming from eigenvalues of random matrices, and is also the sort of a typical limit for turning points in statistical mechanics models. So that if I showed you this phase diagram and I just said this is true, the GUE corners process would be the natural guess for what happens at this point 5. Also, if you commute limits in a way that is non-rigorous, this gives you a heuristic that suggests you actually expect to see GFF type fluctuations up here. Okay, so in summary, we've proved a connection to this model to the GUE corners process. And this phase diagram, the point 4, Evgeni in a previous work showed that near point 4 you also get a convergence to the GUE corners process. Everything else about the phase diagram is conjecture. And I want to reiterate that there's important work to be done in deriving new formulas and analyzing them to confirm this conjectural phase diagram. And it would be especially interesting to get strong enough formulas to analyze this interface between KPZ and Gaussian free field type fluctuations, because they sort of don't even have conjectures for what happens there. We haven't seen it before. Thank you.
Okay, thank you, Mark.
Here's the list of citations. Here's the paper on archive.
Okay, so there's definitely time for questions for Mark if anyone has them. I'm going to stop the recording.